welcome back. Today we are still going to talk about regular plasma, so stability plasmas, and varieties in graphene and the topology integrators. Yes. Yeah. Okay. Yesterday we have introduced the observation of the stability plasmas in graphene nanostructures by using infrared spectroscopy. And then now today we will mainly talk about how to get direct evidence of the stability plasmas in graphene topological indicators. And that is a real space nano-imaging technique. So normally we use SLOM, scanning near field optical scope. So this is traditional SLOM. There's two types of SLOM. One is the FNT with a hole there, and another one is of paper with fiber. So basically, the resolution of this SLOM is determined by the size of this hole or the span of the tapered fiber. So the best resolution is about 80 nanometers, and this kind of SLOM mainly works in in the visible light range. Now, in order to observe the stability plasma in two-dimensional graphene, it has very short wavelengths, so we must have better spatial resolution. So we have to use this new tool, that's the least big scattering SLOM. So this SLOM has many key features. So it has very good resolution, 10 nanometer, especially 10 nanometer. And it has broadband usability. So the lasers, you can use the lasers from visible and infrared to carry us spectral range. So you can basically use broadband laser. And basically it's an A fan, and you have laser FNT. So you have two modules. One is for light imaging to study stability plasma, the amplitude and also phase. So, and another one is light TLR. So it's kind of for a transfer and you can spectroscopy still can get very high spectral resolution. And also surrounding other lasers. So we have different lasers, visible, VIR, VIR, or broadband laser. You can also direct pulse laser into the system. That's the dynamics of the plasmas. So now actually we have this kind of system in Melbourne. So one is placed in MCN. So we have two lasers, one is 633 nanometers, another one is the CO2 laser working at 10 micrometers. And another system is a light FTR, now RNIT. So both of them are just through the leaf found. And how it works? This is a fan, so there's a back scatter laser there to trap the motion of the FNT. But here you have the incident light to the tip. So this laser we illuminate the FNT, and this FNT is coated with metal, so it can say surface plasma. So you have the plasma. So this is the tip we confine this taper structure, confines light into 10 nanometer scale, and this Leo field will interact with the material, with your sample, and modify the elasticity scatter light. The scatter light modified because of interaction between the Leo field and the sample. So by demodulation, so you can resolve what is happening there in the Leo field. So by scanning the sample with this tip, so you can get an optic image. It's a very good resolution. So both the phase and the optic amplitude can be recorded. Now, maybe many of you know these two famous papers which published in Nature back-to-back on the same issue in 2012. The real space observation of the surface plasma in graphene. So one is led by the Professor Barton, and one is by the Collins group in Spain. By the research in the US. Here are a few important signatures for stability plasma in graphene. The first one is fringes. So you can, if you look at the edge, you can see these fringes. That's because of the excitation of certain plasma. Another evidence is the hotspot here. Basically, this taper structure just like it's a cavity. So if you put your FM tip here, basically you can launch surface plasma because the FM tip will compensate the difference between the emitting light and the surface plasma in graphene. So you will launch surface plasma in graphene, and this plasma will be reflected back at the edge of graphene. So the forward and the backward wave in the field is exactly almost standing wave, something like that. That's why you have this interference pattern. So by counting the space between this interference and these fringes, so you can find out the wavelengths. This is the space is half wavelengths of this plasma wavelengths. And the space between these two fringes is half wavelengths of the plasma wavelengths. And this if you work in this taper structure, this tip will launch plasma. Plasma will propagate along this taper structure, just like that in metal. So you can see a hotspot. There are two important evidence. One is hotspot, another one is the fringes. So you can see that see some fringes and some effects. Right? Because it means that these effects can also reflect plasmas. And when changing the wavelengths, so you can see that the hotspots can be moved. So now we talk about how it works. So this is actually simulated profile in the edge. So the tip is located here. So you launch certain plasma reflect at the edge. So you understand the wave. Here is the profile of this standing wave. Basically, plasma dispersion described by this formula, and it's related to the dynamic conductivity of graphene. And the real part of this dispersion determines the plasma wavelengths by this formula. And the ratio between this matter part and the real part defines the damping rate of the plasma. Now, the most attractive thing in graphene plasma is that it's tunable. So in graphene, by electric field or by chemical functionalization, you can change the film level. So you can tune the film level, and you can change characteristics. And here, demonstrate the plasma in graphene can also be tuned. The graphene is placed on top of the substrate, and this tip, you have two electrodes here, so the ion gate. So when you apply a gate, so you inject carriers into graphene. And you can see that the fringe amplitude and periodicity are both enhanced when you increase the L's. So increase gate voltage, you're increasing carrier density. As a result, the amplitude will be increased. And the periodicity, it means the line width, it becomes broader. And as a result, in the real space picture, you can see that the hotspots are moving forward because you have larger wavelengths. And this gate-dependent data for wavelengths and to follow this formula. The plasma is equivalent to the n square, as predicted in the molecular graphene. And we have done some work related to the plasma in graphene, but we are thinking about a different approach. As we have introduced yesterday, in order to launch the plasma in this structure, there's three approaches. First one is to use a breeze. Second one is to use a waveguide. Last one is to have a rock surface operating structure to cut plasma into metal structure. Now we think about waveguide. We make this tapered silicon waveguide and place graphene on top of the silicon waveguide. And but this waveguide normally is used for visible light or near infrared light, not for the medium infrared light with a wavelength of 10 micrometer. So we are trying to excite surface plasma in the leading infrared wavelength range. So this how do we do that? Okay, we transfer simulated graphene on top of this waveguide, and in order to excite surface plasma, we must make sure this graphene thickness is highly doped. So we need to shift wavelength level to very high level. For example, if you go to excite surface plasma at 1550 nanometer, that's a telecommunication wavelength, equals to 0.8 electron volts. So you must make sure the chemical potential can be shifted up to more than 0.4 electron volts. We deposit the simulator of molecular side. So we just put the materials, extract the carriers. We can cause very strong p-type doping in this material. And light is dark from the section, so we direct the waveguide. And this waveguide can cover the high order mode in the surface plasma in graphene. So we perform this Sloan experiments. So this is not this big Sloan, it's a high resolution, just traditional Sloan cable structure. So without graphene, you can only see this optical focusing point. But with the graphene, placed on this taper structure, you can see there's an optical spot, which is even brighter. That is molecular focusing. So that is all the evidence of the surface plasma cited at this linear phase wavelength range. Now we are talking about the edge effect. How the edge, graphene edge, affect the plasma propagation. This is also related to the topological plasma. So, the first look is done by the features group. They have these graphene ribbons, so they have a graphene nano ribbon. So in one ribbon you can see a few fringes. Right? But when the ribbon width is becoming smaller and smaller, eventually you can see a very strong, these fringes can merge together. You can see very strong propagating modes, one-dimensional modes propagating along this ribbon. And they also performed the wavelength-dependent experiments. We found that at a high frequency, so beyond a high frequency, because of the plasma forming damping covering, so this plasma in graphene will dampen very fast. So that's why you can see feature there. When you have the strong plasma, shorter, lower frequency. Now, this paper provides very good overview of the different molecular modes in graphene nanostructure. So over here, to make graphene into this ribbon with different widths. So in the narrow ribbon, very narrow ribbon, you can see this. The first row is the optical image, so experimental result, and all these are simulation results, simulation, and this profile. So for the very narrow ribbon, you can see the waveguide mode here. This waveguide actually is superposition of the waveguide mode and the shading mode. So this shading mode and waveguide mode are dominated by the waveguide mode. And for the graphene ribbon with a bit larger width, so which is comparable to the wavelengths of the plasma in graphene. So you can see this edge mode, the shading mode. So this superposition of the edge mode and the shading mode is dominated by the edge mode. And if I have even broader graphene ribbon, actually this is not ribbon, it's square, graphene square. You can see this kind of feature. Then this is superposition of the edge modes here, this edge modes, and the sheet mode, third order edge mode, fourth order edge mode, and the third order sheet modes. And this is quite interesting. And what we have done is that we also have done some work on the graphene ribbons. So, but it's quite interesting that we're very lucky to get a very long ribbon which gradually change the width of this ribbon. So we can observe all these three modes in one ribbon, one graphene nanostructure. So you have the hotspot here, and also edge mode in the narrow part, and this waveguide mode, so the sheet modes. When you change the wavelengths, excitation wavelengths, you can see the just bright brings bright light, right? We change its length, right? That's because you actually basically change the wavelength of the surface plasma in graphene. Now, what about the edge? How the edge will affect the surface plasma? So here, actually, this is not surface plasma. I show one paper which is about how the edge scatter photons. So when you perform the Raman spectroscopy, so you can find that zigzag edge and armchair edge will scatter the photons in a different way. They have different scattering intensities. So you can find out whether the edge is dominated by zigzag edge or armchair edge. So this expand the work or done some of the simulation on that. So we're going on. What about the plasma? So with an armchair and zigzag edge reflect plasma brightness in a different way. So there's two theoretical papers here. So the basic conclusion is that you can see for the zigzag edge is again this is an energy modes potentials. So same mode for zigzag edge it has lower energy. It means that the zigzag edge will redshift the plasma. So can we do this experiment to verify that? Okay. We collaborate with some researchers in China's academic science. They can grow the single crystal monolayer graphene, and they're using the chemical method to add graphene to this hexagonal structure. And the important thing is that the edge is well known. As identified this Raman spectroscopy, we know that this edge is dominated by zigzag, and this edge is dominated by armchair. And we got this kind of sample and perform a small, found that the zigzag edge is broader fringes here. Right? So it's in agreement with the prediction, the theory. So zigzag edge can redshift the plasma in graphene. Now the applications of surface plasmas. So a few aspects. So first one is polarization control. So you can make polarizers based on the control of the surface wave in graphene. Also plasmonic waveguide, or subdiffraction and imaging focusing. So that's enhanced IR sensing. This one we have done a couple of years ago. So the idea is quite simple. We transfer this multilayer graphene on top of the T-shaped fiber. So it's a kind of hybrid waveguide structure. Graphene on top of the fiber. And the interesting thing is that the light emission from light coming out from this fiber actually is highly polarized. Okay, this is symmetric of the device. So graphene is cross-section view of the fiber. And it is quite different from from the case with metal. So if this has been done, I mean, the metal-based inline fiber polarizer has been done many years ago, maybe in the 1980s, a long time ago. You place thin film gold on top of the D2A fiber, and light will cover in the surface plasma, which is out of plane light, and that will propagate along this film, and then it will propagate to the waveguide. Then you have this, this polarized light, which is vertical, coming out from this device. But in case of graphene, it's completely different. So because now here it's just intrinsic graphene or side loop graphene. So if you definitely not cross light into this wave structure, you have the light wave coming out because graphene is called transfer unit wave. So now, can we make a tunable polarizer? The answer is yes. You will place a neutral field here. So if you get no neutral field, so graphene, field energy graphene is close to zero point. So you have the T polarizer. But if you find the neutral field, for example, using the iron gas neutral chemical doping, something like that, you can get a very strong doping, which is very high level. As a result, you can this graphing single surface plasma, and then you have the TM surface wave come out from this defined as TM on the right. Another application, possible application is for transformation optics. And this is a theoretical paper by some researchers. This work was published in Science. So they pose a simulator graphene on top of this waveguide paper. Basically, it has this is by the gate, and in between has a dynamic material. Because they have different states, distance between the graphene and the by gate. So here, in the center part, space is smaller, and the electric field is stronger. As a result, the doping level is larger, and it has also its plasma. So you can give this straight plasmonic waveguide, or it's called exchange waveguide. Or you place two graphene layers together. Something here, vertical stack graphene, and graphene, dielectric material graphene, so you can see the very strong coupling effect. So what can we do for this? Somebody proposed some enhanced IR photo detection based on this wireless structure. So wireless structure is also quite interesting topic, a really important topic in our center fleet. So we hope to see the dispassionist intelligence in this structure. Another application is to make the focusing, so modulators or resonators. You can place the attenders, so called attenders, on top of the graphene thin film, and make this special structure. You can see the plasma. You have the focusing there. This is kind of focusing of graphene plasma, and probably this kind of different structure is interesting for communication or thinking. So what else can we do by using surface plasma and graphene? So this is one interesting work also done by Professor Bassel's group. They found that the green boundary in graphene, even not visible in AFM graph, but it can effectively reflect the surface plasma. Green boundary normally dominated by stone with defects, or some ring loss or some other kind of defects can effectively reflect the surface plasma. That's why you can see the bright fringes here. This is optic field. So this is AFM tomograph. So AFM tomograph, you can just find out where is the boundary. Even in high resolution TEM, it's really hard to tell where is the boundary between two graphene domains. But here, using the optical method, so you can easily locate the boundary. And this could be very interesting to start the growth of the graphene single crystals. For example, here we show one example. This one is two graphene single crystals merging together. So we can find how they merge together. Is it a boundary? How is it alternate misorientation between these two crystals? So we can look into the and by performing the slot here, and here. Unfortunately, because of the transfer process, we have a lot of bright fringes in this graphene film because transfer into surface extraction and subtraction. As a result, we have made wrinkles. The wrinkles can also reflect the surface plasma. Or another way is to study how these two graphene crystals stack together. Is there any misorientation, and how this misorientation affects the plasma? So here, this saw me from the more layer and from wider. So actually, they scatter the plasma, scatter plasmas in a different way. This probably is still in preparation, and actually, same time, another paper has been published in PR here. Okay, people have also proposed some more transmorphic devices, for example, to combine graphene with metal materials, or place graphene on this plasmonic planetary filters, something like that. And one other thing is for the biochemical sensing. So we know that we can cut graphene into ribbons, and then because it's just like a grating, and it can couple this grating can couple the infrared light into synthesis plasma. Actually, this localized plasma can be used to enhance the sensitivity of this biochemical sensor. So you have localized plasma, and once the chemicals bound to graphene, attached to graphene, you cause you cause the vibration change, frequency change in graphene. As a result, you can see the signatures in the spectroscopy. One similar idea is to place graphene on this grating structure. So this graphene itself is grating, not graphene, based on grating. It can also enhance the sensitivity of this kind of biochemical sensor. Now we talk about the topological plasmas in graphene. So why graphene? So because graphene supports very large tunable calorie density. That's the reason. Secondly, it is a small tunable drift bands, allowing high cyclotron frequencies up to tens of terahertz range. And high quality graphene can speed exponentially long transcription time at very long transcription time to the picosecond range. So all these properties make the topological plasmas to be observed at a very high frequency or short wavelengths, non-propagation lengths, and in large topological band gaps. This one, I can give you two examples. So this first one, so one recent publication in physical refrigerators by the Lecture2 group in UC Berkeley. So what is the challenge? The challenge is that normally the topological gap is only below the cyclotron frequency. Okay, the spectrum operation remains limited to lower frequency. Now, by simply engineering the graphene in this lattice structure, the periodic nanostructure 2D mononuclear graphene, the operation frequency of topological plasma can be dramatically increased to tens of terahertz. So, and still have a very large gap ratio. So you can have a very small magnetic field. And here is the edge dispersion of this graphene superlattice. So at zero field, all the edge states are non-topological, the no edge states. All the edge states not topological. But if you apply a field for Tesla, you have the topological one-way edge states appear in the band gap. Very hard. That is topological edge states. And it finally doping the system supports topological tripod band gaps with mid-gap frequency to the terahertz range. Here, I'll show you more pictures. So how to decide how to notch the topological plasma in this kind of structure? So imagine we have the dipole emitter here. This is the edge. This is the dipole emitter. The diameter have the frequency of 40.6 terahertz. That is in the gap center here. That is in the gap center in 1 and 2 bands. So you can see besides the edge plasma is 0. So if there's no electric field, actually, if you apply electric field 4 terahertz, 4 Tesla, you can see that the edge stays with power grid unidirectionally from left to right with constant magnitude. And it's very unique. And further, if you make a disorder here, disorder defect, you still can see that the edge stays pointed from left to right without backscatter. So that's the evidence of topological plasma in graphene superlattice. And another research group in China proposed another idea to use this superlattice. and try to demonstrate the topological plasma in graphene structure. This a bit different honeycomb superlattice structure. And okay, they found that highly confined topological protected edge stays at the infrared frequency in this empirical structure at a very low magnetic field, and also have the bond stays in the have the topological protected stays in also localized dark modes here. Here we show the band diagrams of the graphene superlight lattice. So, there's a magnetic field of 4 Tesla supplied, so we have a large band gap, and it's opening. No electric field, just visible band gap. So we apply electric field, so back to opening. It's 0.0 kK prime. So we lead to the localized dark modes within the band gap. And then also simulate the topological protected plasma in the edge in a complex structure like that. So it's a graphene structure. So if there's a electric field, there's a magnetic field, one source of energy, basically, this structure announced the topologically protected plasma at the edge of this structure. And if you inverse if you change the sign of the magnetic field, so this is the direction of the propagation of this plasma is reversed. So we have reverse direction. And it's pretty interesting to see that there's no back reflection is at the core. So you can allow the one-way propagation of this edge. Is there any more experimental evidence to show the edge effect on the topological plasmas? I did just one work 5 years ago by IBM researchers. They make micro disks of graphene and they also apply the magnetic field. And they found that both dark modes and edge modes. I think this is something quite close to the topological plasma because they can see that if you have a large electric field, you can see the split of this mode, edge mode and dark mode. And the edge mode has longer lifetimes in the high field. So, can we find this most direct evidence for the topological plasma in this kind of graphene superlattice? Probably we need to do Sloan and the magnetic field to get the real space evidence. Okay, now we talk about the plasma in topological insulators. So topological insulators mainly these families of materials in basement telluride with some lean tellurides. So yes, this is the latest structure. And a couple years ago, actually, just one work, similar idea to that in graphene, they cut bismuth telluride into grating structure. So first they grow the large area bismuth telluride, and then you using this scraping method to cut the ribbon, and then perform the in-phase spectroscopy. So by changing the width of the ribbon from the line width of the plasma will really constant. So even at low temperature and low temperature, low temperature. So as this is expected by the design, topology carriers explained. And the phonon frequency here is green. You get the green trace. So it's phonons. So that's not change if you change the width of the plasma. And the plasma, the line width, okay, actually, this plasma line width can be changed if you change the width of the ribbon from 2 micrometer to 8 micrometer. So if you have larger line space, you have a narrow, larger width of the ribbon. You have a narrow line width of the plasma resonance. And also you shift to lower frequency. And also, same group, they claim that they have found the topological protected Dirac plasma in the similar structure as gradient structure. And here's the light, which is polarized light, equal to the gradient. And I think the most important evidence is shown here. They found that, so firstly, the plasma frequency is nearly independent of this doping element, indium. And the plasma width has a sudden broadening here, sudden broadening in this region. That we call the topological transition region. So you see this kind of, because of the single particle behavior. And also last research by the same group from Italy, and they found some evidence of the macroplasma in this missing line. So this is topological insulator. So now they apply electric field. So this light is the electric field. And they found in the low electric field, the synchrotron resonance is well separated. Not going electric field separated from the magnetoplasma modes here. Okay. So we have also done some research on these topological insulators. So we know that both graphene and topological insulator can support the Dirac plasma. So we try to address the question: what will happen if you put these two materials together? So you form heater structure. What will happen? What can you see? Similar idea. So we have the silicon grating, and then we transfer graphene on top of the grating, then grow a outer layer of bismuth line. So this is the picture of the material. And then we form the FTIR, for transfer infrared spectroscopy. So we check the absorption in the wavelength range. It actually guarantees transmitter difference. The peak represents the resonance here. We found that just for the bare graphene, the resonance amplitude is pretty small, about less than 10%. As we discussed yesterday, the 1A graphene have limited absorption. And now, if you make a heater structure, the resonance is 4 times stronger, and also because of hybridization of these two different plasmas, the resonance peak will shift to lower frequency range. Also, there's some other research on the plasmas in topological insulators. I don't know whether we can call this as topological insulator because basically it didn't. I mean, this kind of material, and they didn't mirror. I mean, they don't have the evidence of the topological status of this material. So, but they count this material into these materials nanostructures to make the nanosleeves array here, and they can see the visible plasma resonance, so in visible range. Or you can further make the grating structure. But this nanosleeve array, so you have the resonance in the visible range, 400 to 600 nanometers. And also, you can cut this material into grating, so you can also observe this plasma resonance in all visible range. Actually, this material is quite interesting. Our collaborators in Singapore have done some research by using electron beams to inject plasma in this material. So basically, they grow the material and check the using the TEM-based electron energy loss spectroscopy. They can do the mapping, plasma mapping of this material, and found a very broad peak here. That's because because of plasma absorption. So, and if you change the energy, so you have you can actually map at different energies. So they can find different modes having the entire visible range, and the visible plasma can be tuned by doping as well. So this is energy, change the energy. Now if you change the material using the sending to doped material, you can also change the absorption, osmotic plasma absorption in visible range. And I think this kind of plasma effect largely depends on the quality of the material. So if you have the highly crystalline crystal, you have this peak. If you heat up the material to a certain temperature or use some other project to damage the crystal to amorphous or polycrystalline, basically the plasma resonance will be decreased. And if you use a chemical method to recrystalline to recrystalline of the crystal, this can recover the plasma resonance. That is quite interesting using the evidence that the plasma depends on the quality, crystallinity of the material. Now I'm going to show some Leo field experimental results of the plasma in topological state of bismuth tungsten. I think we started this work a very long time ago. We were still postdoc in Singapore. Because this is the first picture we got 5 years ago, I think more than 5 years ago. Okay. This topograph is an optic field. Okay. It's very interesting to see there's a bright fringes outside of the crystal. So according to this profile, this is bright fringes. It's at the end, it's at the edge outside the crystal. And we first found that this phenomenon, okay, sorry, yes, I have more slides here. We changed the expectation wavelength and found that whatever the wavelength is always have this edge modes here. Outside, at the edge, always have white fringes. And we first changed the thickness. Okay, we found that this white fringes is thickness dependent. So in the single samples, you have stronger, larger amplitude. And we first gated the material, gated the single crystal by gate, trying to inject the carriers into this material. And similarly, we can find that the amplitude can also be changed, not only in graphene, so you inject carriers, and in the plasma amplitude also be tuned. We know that this kind of edge mode, what do we have if you place two edges very close to each other? Is there any inference or enhancement? Then we look into this sample is a gap. So it's a gap. So in the gap, we did see the enhancement in the field. I mean, actually, the recent gap gradually changed. This is not fixed. So at different location, you have different profile. It's very in the narrow region. So you have these two bright fringes at the edge. We merge together from a very strong one. I also noticed some other research on the Sloan measurements of this topological insulator. This family of materials. Okay. But you see that they didn't observe the bright fringes outside the crystal, and we have verified that on different materials and found that the crystal quality is really important. I think for this research, mainly because the material was inside, but the chemical research, so the thermal is inside that place. The quality is not high enough. But the good thing is that by using this Sloan technique, you can visualize the localized chemical density in the crystal. So these crystals, you can see different contrasts at different regions. Right? And that may tell you some facts about how these crystals grow, and the distribution of localized carrier density can also tell you the doping of this material in different places. So the last part of this talk about the other forms of patterns. So we know that metals support surface plasma patterns, and the electro material can support formal patterns, and some semiconductor material, so TMT material can support external patterns, different forms of patterns, and this is very good overview of the different forms of patterns in 2D materials. So first one is surface plasma pattern in graphene, and later you found that the dielectric material or nitride can support formal patterns or in insulators. And quite recently, I think early last year, the external patterns also demonstrating TMT materials. I think there are a few research articles in major journals. Most of them are using the spectroscope method, and they place TMT material into the cavity. You can observe the external patterns, and this one research is about the near field observation of the external patterns. Wouldn't depend upon the same light. Now there are two more forms of patterns to be demonstrated, to be observed. Topological patterns or magnet patterns. So in magnet materials or in materials. So this is what can we do? What's the application for these patterns in electric material? So this is one example. Patterns, hyperbolic patterns in monolight. That is useful for the subdiffractional imaging or focusing. I don't know the details. I just have maybe other materials can support hyperbolic patterns beyond monolight. The monolight is it's a symmetric structure, chemical structure. Patterns it's hyperbolic, but it's atropic in plane. So can we find some other materials we can support atropic patterns, so you can direct besides the pattern in a certain direction? That would be very interesting. And now excellence in TMT materials. So this is also a useful picture to of the gap of different 2D material, TMT materials, and as well as the exons, or the exon, you can figure out exon energy. This useful figure. So 2D material actually is a very good platform to notch and visualize different forms of patterns. So plasma pattern, form pattern, external patterns. There are different approaches to notch patterns. So, for example, the grating structure or tip, the small tip notched plasma, or electron beam notched plasmas. Okay. The applications of future opportunities for these patterns in 2D materials. First one could be the net trafficking, so 2D optics, flat lens, flat optics, subdirectional focusing, or you can also integrate the 2D material graphene with a semiconductor with a waveguide to control to realize the modulators, QC lasing, terrace lasing, and this plasmonic effect can also be used to enhance the sensing, improve the sensitivity of the biochemical sensors, or in the area of nonlinear optics, so you can use the plasmonic effect to enhance the harmonic generation of some lasing. Okay, that's all. Thanks.